cannot, when you get to H3, say this is equal to H4. Because third-party reader are going to say, why H3 is equal to H4? This is what you're telling them why. So again, it's all come down to the communication, how well you communicate with a third party. By writing this statement saying because of the expansion valve, delta H cross the expansion valve is equal to 0, therefore H4 and H3 are the same. That's the only way. If you don't write that and you just write here, it's equal to H4, you don't get a point for that. You lose points. Even you have a correct answer, but you didn't explain why. And again, I'm focused on your engineering process, not your answer. So you don't get any credit for that. So be very conscientious of that. Once you have all the H values, you plug it in and you find the work of a compressor, QH, QL, whatever needed. Definitely QL. Most of the time, we don't care about QH. Just work of a compressor in QL because we want to plug it in here to find the coefficient of performance. That is one way of having actual cycle. Now, there is another way of having actual cycle. That's, again, comes down to spending a little time, 30 seconds more time, reading the problem slowly and carefully. If the temperature and pressure at point 1 is given, then your TS diagram is going to be different. If temperature and pressure at point 3 is given, then your TS diagram is going to be different. So be very careful and pay attention to that. Now our point 1, it's going to be here in a superheated region. And point 3 going to be in a compressed liquid. Then you come down again to point 4, connecting it back to point 1. In this case, you have to have the temperature and pressure. You always have the pressure at point 1, but you need another point of reference, and that's the temperature. Because you no longer can say X is equal to 1, because it's not. That point 1 is in a superheated. The only way you can find that value to have those two reference points, pressure and temperature, to find the value H1 as a superheated. Similarly, here you have to have temperature and pressure at point 3. So be very careful, read the problem carefully. If that's the case, your TS diagram is going to be totally different. If you don't do it this way, this has a 10 points, you're not going to get the point. If you do the TS diagram for ideal cycle. So be very careful. Now, if there is efficiency involved in this case, once again, this becomes 2A, and you show that efficiency of compressor on your diagram. Now, one thing I didn't talk about, if in the case before, this becomes H2S, which we don't need, then what you need to do, use the efficiency of a compressor which is equal to H2S minus H1 divided by H2A minus H1 to find the actual H2A value. Once you find it, on your calculation, you need to include those. Whatever you have for work of the compressor becomes H2A minus H1, not regular H2. You cannot use the H2S value. You have to use the actual value. Now, if we have this case at point 1, we have a pressure at point 1 and a temperature at point 1. Now this time we go to superheated table. Now H1 is just H value from the table. It's not H of G. And that's the value of S1. At state 2, remain the same based on P2 and S2 equal to S1. You find H2S using this efficiency of a compressor. You find the actual value at point 2. At state 3, we no longer have X3 is equal to 0. So you have a temperature. But you are in a liquid side, and you find the H3, which is H of F on that table, and that would be your H3 value. When you get to state 4, again, you write that statement, you find the H4 value, you're all set, and then you go back here, find the work of a compressor, QL, plug it in here, and you find coefficient of the performance. So there are 2 scenarios when it comes to actual refrigeration cycle. And it all depends. The first scenario, if you don't have any temperature for point 1 and no temperature for point 3, that means you're starting at the saturated vapor. And you stop at saturated liquid. However, if the temperature and pressure are given, your point 1 is a superheater. Your point 3 is a compressed liquid, which using the same saturated liquid table, but the location of it would be different, and you have to show it correctly, otherwise you don't get credit for it. Do you have any questions?
Professor?
Yes.
So just so I understand, when it comes to point 3, when we have the pressure and the temperature, when we look for H of 3, it's going to be H of F for the value?
The H3 would be H of F regardless of whether it is in saturated liquid or compressed liquid, that would be H of F from the saturated liquid table.
Oh, okay. Thank you.
If you remember, we talk about this on a power cycle, that the saturated liquid and compressed liquid, the value of H are so close that we really did not create another table for a compressed liquid. So whether you're located in the compressed liquid or saturated liquid, we have only one table for it, and that's a saturated liquid table. Since you are on the liquid side, you use H of F. If you're on a superheated, the superheated table doesn't have H of F or H of G or any of those. You just have H, that's it. So you just find out H value and S value. However, if your point 1 is located on the saturated vapor line, you look at saturated liquid table, but you find H of G and S of G because that point is on the saturated vapor line. It's not a vapor yet. It's not a superheated vapor. So that's where you find that H value. That's what I did the first time. Did that answer your question?
Yes, it did. Thank you.
No problem. Now, there is one more thing about refrigeration cycle. We're doing all this work because our focus is to find the QL. Once we calculate it, we need to do something with it. We can use it as an air conditioning, cool the air. We can use it as refrigeration, like a refrigerator at your home, or a large refrigerator in a restaurant, or a supermarket, or a warehouse. Or we can make ice with it. So there is something going to go on here. So if we go back in the equipment arrangement, we can introduce air or water and get cold air. We can get cold water, or we can get ice. That would be the product that we're looking for. So we're doing all of these things to get something out of it. If we want to use it for air conditioning, this is what we do. If you want to use it for just regular refrigeration, again, we use air because if you open your refrigerator, you can see the air flowing through the refrigerator and keeping everything cool. And that's what that is. Now, if you want to have ice water, cold water, so that's how we use it. You know, those water fountain that we used to have in the school, we don't have them anymore because of the COVID. That's the refrigeration cycle, giving you cold water to drink. Now, if you want to make ice, to have an ice machine, or in case of your home refrigerator, the section of the refrigerator that make ice, then again, we can introduce the water to it and get ice out of it. So read the problem carefully and see what it's telling you. They either tell you they add water into it or air. In either case, our QL that we found here has to be equal, that's the energy balance equation, to the Q, let's say, of water or air, whatever the case is. So that is the important part that you need to stay focused. We know what our QL is. Our QL is the mass of refrigerant times H1 minus H4. For the other side, we can use the heat transfer equation. We can say the mass of water times Cp of water times delta T, T2 minus T1. So that would be T1 here and T2 here. Of course, T1 of, we can say T water 1 and T water 2. So this way, you don't get confused with any temperature at 0.1 or 0.2. So if you already have the mass of refrigerant, you already found H1 and H2, H4, you can have mass of water, they ask you to find the delta T. Or they give you delta T, they give you T2 and T1, they want you to find the mass of water. So that's, this relationship will make things work. So watch out for that. After you've gone through the exercise, whether it's ideal or actual or this kind of actual, it doesn't matter which kind. At the end of the day, once you find your QL, then you put it equal to the Q of water or air that it's connected to that. And that's what you write down. Any questions? Please pay attention to this because it might be part of the exam and I don't want you to lose that. If you have any questions, not clear, please feel free to ask. Now, similarly, this QH, the condenser just doesn't do anything unless we use external material to remove the heat. We can put a fan at the top of the condenser and remove the heat by air. Or we can connect the water to it and get the other hot water out from the other side. So we can have air or water coming into the condenser and hot air or hot water going out of the condenser. We need to use the same logic that we used here for the condenser. It's the same logic. So in that case, our QH in that case, our QH has to be equal to the Q, let's say, of air. Now, again, this side would be the mass of refrigerant times H2A minus H1. On the other side, this side, we can use heat transfer equation, the mass of air times Cp of air times T2 of air minus T1 of air. So that's similar scenario that we have here, we can have up there when the QH is equal to Q air. If it's water, that would be Q of water. Then CP would be CP of water, not CP of air. So one side we have a thermodynamic equation. On the other side, we have a heat transfer equation, and we can solve the values. So watch out for these two additional scenarios on the refrigeration cycle. Any questions? You guys are making it easy. This is the last day of the class for the whole semester. I was expecting you guys just come at me from every angle, but you're very quiet. Okay. Is there anything else you want me to do on chapter 11? No? Okay. Well, we have almost half an hour. Do you have any questions? on chapter 9.
Yeah, I got a question, Professor. In terms of
Sure.
like refrigeration versus heat pump, is it really just like the direction it's facing, like which side the QH or QL is?
It's
Is
the
it
same thing.
operation?
It's basically, it's the same operation that you see here. And a heat pump is focused more of the QH than QL.
Yeah, so your product is the outgoing hot air or water in that situation.
Right. So on a heat pump, the COP of a heat pump is equal to the QH divided by work of a compressor, opposite of that. Because in a heat pump, that's what we're looking at.
Got it.
Okay. And again, heat pump is a kind of a unique scenario because you can use a heat pump during the winter and get a heat out of it, recover the heat there. And then you can use it during the summertime and recover the QL and just use it for air conditioning. That's the beauty of it. So that's why the heat pump was invented, and we use it a lot today in air conditioning for homes. We don't use a split system anymore because it's more efficient to use a heat pump. Because at your home, if you have air conditioning, you have air conditioning unit in your garage or your attic, and then you have your condenser outside in the backyard. And then you have a gas burner heater separately, and they're all controlled by the thermostat. So you put it in heat mode, then your heater starts working and provide heating. You put it in your cooling, then the condenser will kick in and your compressor will kick in and provide the cooling for you. That's called a split system. There are more than that on the refrigeration side. We have package units. The package unit has everything all packaged in one unit. We generally do not use that for residential. That is used for commercial. Most of the small commercial shopping centers or buildings, they have package units on the roof. If you're in a ECS building, go to one of the rooms like 202, 204, or whatever, facing Palo Verde Street. Then you see the maintenance facility. When you look at the maintenance facility, on the roof of maintenance facility, you see a bunch of units, boxes. Those are the package unit that has air conditioning, heating, and everything in that package unit. It's all there. The condenser, the compressor, everything is all in one package. Those are used for small commercial or facilities like maintenance facilities in our school. The other part, it's called central utility plant. That's where things are going to get really big. You want me to talk about that? I guess you want. That's the general information. Now, nothing to do with chapter 11, so don't get crazy on that. Now, for our campus or very large high-rise building, hospitals, we use a concept called central plant. The central plant is basically, you have a bunch of equipment that's called chiller. Like in our school, they have 3 or 4 large chillers. The chillers are basically a big, huge heat exchanger equipment that has the evaporator unit and it's got compressor unit and the condenser is completely outside. So the work of a chiller is basically you bring the water from outside and you get chilled water out of that. Now, once you get that chilled water, you pipe that, you insulate it. This is about 49 degrees Fahrenheit temperature. And this goes to various buildings. If you look at the top floor on the roof of our own building, let's say ECS, you'll see a box that is called air handling unit or AHU. Now, this chilled water comes to this air handling unit. This air handling unit has one fan and two coils. One coil is a chilled water coil. One is a hot water coil. And the air from outside will blow over this chilled water that has gone into that air handling unit, and you get cold air coming out. And we put a ducting and goes to various classrooms, so we have air conditioning. That's during the summertime. Now, this chilled water goes here and then comes back to the chiller again. We cut off this water from outside. So we create a loop that this just keep on going back and forth. From the hot water side, there is a boiler that the water goes in. And then you have hot water coming out. And that goes to this coil. During the winter time, this coil is off by the thermostat. This fan will work, go through this hot water coil, and you have a hot air this time coming out to the classroom. And then whatever left over is going to come back to the boiler. That's another loop that we create. So just keep circulating so we don't use this water anymore from outside. That's how in the larger system, facilities, this is what we use in order to provide cooling and heating for large facilities. Because we can't just put heat pump in each classroom. That would be so expensive and it's hard to maintain and control it. But in this scenario, there is a control system called energy management control system that controls all the activities of various chillers and various boilers. Of course, keep in mind, there are a whole bunch of other equipment involved. The water comes up here, cannot go all the way to the top floor of a ECS building. So we have a chilled water pump that will pump it all the way up there. And we have another pump to bring it back to the chiller because of the distance. Because this comes down, goes underground, everything is underground. It's underground, come to the, 3 feet away from the building, and then it will go up, and then same thing, this goes down, and then come back to the chiller. So we have various pumps to pump this chill water to various buildings. And same thing here, we have a hot water pump to pump the water to various buildings and bring it back. So this becomes very, very sophisticated. It requires a lot of work. And the condenser that we use for the chiller, that is what you see it outside. It was a big, huge equipment, and it's called cooling tower, which uses water to remove the heat from the refrigerator inside the chiller. That's what that is. And this cooling water has its own pumps, pump 1 and 2 and 3, sometimes 3 pumps in order to circulate all those water. Depends how many chillers you have. If you have 3 chillers, you have 3 pumps here. If you have 2 chillers, you will have 2 pumps. So it gets very sophisticated, very complex. And not, if you get into that business of air conditioning design, one of the things that you must learn is this, because the majority of your customers are government agencies or schools, military bases, hospitals, high-rise building, they all have this kind of a system working. So smaller, small shopping centers, small commercial facilities, they don't use this, they use a package units, then you design it the other way. So as an air conditioning designer, you need to be familiar how to design a small air conditioning for the home, how to design a smaller air conditioning for the small commercial facilities, and most importantly, how to design a central plant that provides cooling and heating for large campuses. So that's a great field to be in. Not too many people specialize in this, unfortunately. The engineers who are into this, they're making tons of money because they're unique, they have a unique expertise, and people, companies like us, we go to the conference, various conferences, shows, expositions, and we target those people who are expert on this and to hire them. Because it's hard to find the expert in that field. So that's something, if you guys are interested in design, this is something that if you get good at it, one of the instructors, part-time faculties, my colleague, my friend, Dr. Hank Bagheri, he's specialized on that. He's retired now, but he does consulting once in a while. Every time the big companies get into trouble and they can't figure out what to do to, fix it or design it, they call him, they say, hey, we need your help. And it's a big, good money. He charge them, I don't know, $400 or $500 an hour to just go there and help them out. And they will pay him with a smile in their face because he can solve their problem. And he's retired, he just teach one or two courses at Cal State Long Beach and kicking back and relaxed. That's another field that if you guys might be interested. It's a very fascinating field, extremely fascinating. I just gave you a little bit of a highlight. Once you really get into it, you see how fascinating this field is and how interesting it is. Anyway, do you have any question, any of these that you want me to explain? No question. By the way,
Yes.
oh, go ahead.
Oh, no, I was wondering, so like in the normal home, we're just pushing air around instead of, in this case, water. Like, what's the advantage of, pushing water around to, like, I guess, hold the energy versus, just having like air vents?
Well, the home is not worth spending effort to push water around. There is no reason for it because it can be done much cheaper, much easier, much simpler. Because for the home, you don't want too sophisticated system there because then they can afford to have somebody to repair it and maintain it. And they don't know how to work it out. So air would be the easier way. And that's why we have those units that we just push air and do the cooling. Get outside air, cool them in, bring it inside the home. And we try our best to recirculate the inside air up to 70, 80% of it and get 20% fresh air all the time. Because it's not healthy if you just recirculate air 100%. Give you an example. What is the problem with airplanes? If one person is sneezing in an airplane, all the passengers are going to get sick. The reason for it, because airplane is circulating the air 100% all the time. Because they don't have any way of getting outside air into their system and release some of the, circulated air away so they can always have a fresh air. So that's what the problem with that one is. The opposite of that is a hospital. Hospitals, by law, they always have to have 100% outside air. Because if they circulate the air to the next room, the guy in the next room has a heart attack and this guy has a flu, and the guy in a heart attack cannot afford to have a flu because he's going to die. That's why they have a unit that is 100% getting outside air, cool it, and then send it out, cool it, and send it out. There is no loop that keeps circulating. So that's benefit of a hospital, and that's a problem with the airplane. So that's what it is. But in a home, it's always designed to constantly have a 10% minimum outside fresh air. In a commercial building, it's a 20% outside air. It keeps coming in. So using the water for smaller commercial buildings or smaller homes, it's not an efficient way of doing it. Not at all. Did that answer your question?
Yep, got it. Thank you very much.
Oh, not a problem. I'm glad you guys are thinking outside the box and asking these kind of questions. The more questions you ask, the more challenging it's going to be, and I love that. So it's great. I'm glad you guys are into it. And even this might not be your future, or you might not be concerned about this, but just thinking about it and asking the question, it shows that you have the engineering mentality, that you always look at both sides of a coin. The coin has two sides, not only one. And the more you look at things and you're thinking outside the box, learning to think outside the box, the more successful basically you become. And I probably told you this. I hired an intern from one of my students at Cal State Long Beach. And he graduated, he became full-time, he got his master's degree, he's got his PE, and in a very short period of time, in just 6 years, he became a vice president of our company. And now I'm planning to retire from my company next year, and he's going to be the president of replacing me. And this happened in 2012. And we are in 2022, let's say. In 10 years, this guy just went up exponentially. He got his master's, he's getting his MBA next semester, he's going to finish that. So he's got a good head in his shoulder, and he's always thinking outside the box. And when I was his advisor when he was writing his thesis, he wrote the thesis that it's a combination of electrical and mechanical system. And I approved that. And the funny thing is, the College of Engineering, the assistant dean, had a hard time understanding why the mechanical engineer is designing electrical distribution system with renewable energy involved in it as his thesis. Why is doing all the electrical part? He's a mechanical engineer. That's how good he was, and he is. And that is impressive. So within the 10 years, he just went up so high that what I'm trying to tell you is it's all going to come down to you. How fast you want to go, how good you want to get to a, upper division, upper level of engineering. Engineering design is great. The first 4 or 5 years, whatever you do, manufacturing, aerospace, whatever you do, you're going to get good at it, and it's fantastic. But my recommendation to you is definitely go back to school, get your master's, because it puts you in a different level, in a higher level. There was a time that if you had a high school diploma, you were great. That was before I was born, of course. Then there was a time when if you had a bachelor's degree, you were God. Now, everybody has bachelor's degree. So if you have a master's degree, you're one step ahead of them. And then when you start working, whatever work you end up to do or you like to do, try to keep an open eye and push your ego, like keep on asking your boss for more assignments. That's what I did when I started my career. And get more and more and more. So you get exposed to more of the things that your company is doing. And the more exposure will open more doors for you. And after 5, 6 years of doing engineering work, you want to get into the management level. Now, a lot of you saying, I don't like management. I love technical aspects of it, and I like the engineering side of it. Yes. When you're a manager, that doesn't mean you're not an engineer anymore. But the beauty of it is you get to a point that now you're no longer a task-oriented engineer. When you're doing engineering, somebody will give you a task and you will do it. Now you are that somebody. You are the manager. You make the assignment to other people. You're telling them what needs to be done. Now, when you have 4, 5, 10, 20, 100 people working under you, then you have to have 100 different assignments. So that means you, as an engineer who now become a manager, you have the ability to run 100 things at the same time. And all engineering work, it's not anything else. You're not managing the office or buying the furniture for office. You're managing a whole bunch of engineers. So you have to have the ability to think about what is this guy doing, what is that guy doing, what is the other person doing. So that makes it great. And then you move up to a higher level vice presidency. Then you have the responsibility of running a region. Or you become a senior vice president, then you're in charge of a division of the whole company. So there are so many opportunities as you go higher and higher. You never lose your engineering capability. You're enhancing it. You may not sitting behind a computer and doing the actual design. No, you're not going to do that when you get to the management. But you become much more creative and coming up with all those conceptual ideas. And those conceptual ideas, when they become real and become a real project and it's done, and you get a big, huge kick out of it. I drive around LA area, Orange County area, and I see some of the things that I've done. I always look at the building or look at the site and I say, oh, this is what I did. Oh, I did this one, I did that one. I go around the country doing the same thing. I've done work in New York, in Connecticut, in Chicago, Denver, Atlanta, Huntsville, Alabama, San Francisco, of course, San Diego a lot, LA and Orange County, obviously, Arizona, Nevada. Well, guess what? Las Vegas. And it's amazing when you go, and when I go to Vegas, I don't want to stay in Paris Hotel because I did work there. But every time I pass in front of a Paris Hotel, I look at it and I remember what I did for them. So it becomes amazing, adventure as you go up, as you put 10, 15 years into your engineering work and you get to that point of a management position, you're going to get big kick out of it. You want to have something that you enjoy for the rest of your life. Every time anybody asks questions about it, anyone would talk about San Diego Airport, I can stand in front of them and talk for 2 hours what I did there. Or LA Harbor College, LA Southwest College, LA Unified School Districts. So I have so many stories that I can tell, the things that I've done. And one day you want to get in my position and you have lot of stories to tell the next generation of engineers. So just keep pushing the envelope. Don't get to the stagnation point that, oh, I like the engineering and I want to just be an engineer for the rest of my life. That's a very wrong approach. because you're going to be focused, task-oriented guy who does one thing and one thing only. That's not good. You get tired after. Even though you enjoy doing it for the first 3, 4, 5 years, when it comes to 10 years, you're sick and tired of whatever it is. You don't want to see it anymore. So keep that in mind. You have a bright future, great future ahead of you. Capitalize on it, move forward. Don't let anybody or anything stop you. That's my 2 cents into it. Again, it was a pleasure serving you guys this semester. I did my best under the circumstances. I'm not a perfect guy. This was not a perfect scenario, by no means, but I did the best under the circumstances. I tried so many different ways when the pandemic started. We had this camera, putting it on a paper, and I write, and people were complaining we cannot see it. And I had to put 2 pages next to each other to show them TS diagram and equipment arrangement. It was just painful. So I learned about the camera. The first camera I got wasn't that good. So a lot of complaints. There were a lot of noises, background noises. Then I got another camera, which is this one. And got the board, put it in my office, and put it 3 feet away. As you can see, I'm just, my movement, if I come this close, I'm just hitting my laptop. To do the best I can. And I did. Again, as I said, I'm not perfect. I'm not saying this is the best thing ever happened to you guys. No, it's not. That's the worst thing that happened to you guys. Hopefully next semester, as I heard, I got an email from the school that we're going to have an in-person classes, which is great. Go back to school. And I hope that I contributed a little bit to your enjoying, adventure. I wish you all the best. And I'm always available to you guys. Now you have my email and everything. So don't hesitate to email me down the road if you have any questions or any issues or any problems. I'll be more than happy to help you out. And hopefully I see you guys next semester. If you're running around the campus, come and knock on my door in my office. My office hours is always there. So if you're free, stop by, sit down and chit chat and catch up. So have a great final week, which is next week. And I'm sure you guys are going to do great. And I wish all of you the best. With that, thank you and see you guys there.
Thank you, Professor.
Thank you, Professor.
My pleasure.
Professor.
Thank you.
Thank you.
Thank you.
Professor, would it be possible to speak with you after class?
Do it again.
Would it be possible to have a word with you after class?
Where did I what?
Would it be possible to have a word with you after class?
Oh, after the class, of course, I'm here.
Okay, I just had a question.
Yeah, you can stick around. You can stick around and ask me the question you have. Not a problem.
Okay, perfect.
Sure.
Thank you, Professor. I really enjoyed the class. And I
Thank
appreciate it.
you. I'm glad that you liked it. Thank you.
All right.
Professor, this
Take
was
care.
a very enjoyable class and learned a ton. So thank you very much.
Thank you, Arthur. Appreciate that. Thank you.